Now let's discuss different types of relation. We start with the most basic one, which is a void relation. If you recall from set theory, if a set contains no elements, we simply refer to it as the null set. Right. So here, let us suppose we have a set A. Let A be some set, and we have this null set, which is a subset of the Cartesian product of the set A with itself. Then in that case, we can simply say that the null set is a relation. This is a relation on A. That's the definition of a relation. Now, what is phi? Phi being a null set, this simply means that this particular relation is going to be a void relation or simply an empty relation. Now, to best understand this, let's take an example. Let us suppose that we have a set A. Set A contains the elements 3 and 5. And then we have another set B. B contains a single element. Let that element be 7. Okay. Now, we're going to define a relation denoted by R. So what is R? Let's say R is a set containing the ordered pair A, B, such that we have A belonging to the set A and B belonging to the set B. And then we have a relationship between A and B, the relation being A minus B is an odd number. So when we take the difference between A and B, this is an odd number. Fine. This is an odd number. So let's verify if this is true or not. So since A belongs to the set A, we're going to pick up an element from the set A. So let's say we pick up A to be equals to 3. And we're going to pick up an element from the set B. So since B has only one single element, we're going to pick up 7 only. Now, what is A minus B? Now, this implies that A minus B, that's 3 minus 7. So 3 minus 7 corresponds to negative 4. But negative 4, this is an even integer, even negative integer. Next, if we consider A to be equals to the second element 5, B, since there's a single element, we consider B to be equals to 7. So this is going to give us A minus B. So that's going to be equals to 5 minus 7, which gives us negative 2. Now, negative 2 is also an even integer. Now, our goal is to find out an odd number, or you can say an odd integer. Now, since after performing the subtraction, we are not getting a single odd number. So what is R here? R is here is nothing. There will be no such ordered pair. So this simply means that this is an empty relation, or we can say a void relation. So let's move on to the next type of relation. Now, the next type of relation is going to be referred to as the universal relation if for some set A. So let's say let A be some set. So let A be a set. Now, if we have the Cartesian product of the set A with itself, which is also a subset of the Cartesian product of A with itself, then in this case, what we did, this definition simply tells us that this implies that A Cartesian product with this same set itself, that is A, is a relation. This is a relation on A. This is a relation on A. And when this is the case, we can simply say that A is nothing but the universal relation. Now, we can best understand this with the help of an example. So let us suppose we consider a set A to be containing two elements A, B. Okay. Now, let's take the Cartesian product of the set A with itself, which means we are taking the set A containing the elements A, B, and we're trying to find out its Cartesian product with the same set A, which also contains the elements A, B. Now, this Cartesian product is going to give us 4 ordered pairs, since each of them has got 2 elements. So we get the first ordered pair as A, A. Next, we have A, B, followed by B, A, and then we have B, B. Fine. So this is the Cartesian product of the set A with itself. So if we consider the relation R to be simply the Cartesian product of A with itself, and this, what does it mean? This simply means that since the Cartesian product of A with itself is going to contain all of these 4 elements, it must be true that R is a subset of Cartesian product of A with itself. Okay, so that in that case, this relation R is going to be referred to as the universal relation. This is quite trivial. Okay, now in the void relation and in universal relation. Now what we can say here, that the void relation or the empty relation, that is going to give us the smallest relation on A, whereas the universal relation is going to give us the largest relation on A. That's because the void relation does not have any ordered pairs, whereas the universal relation is going to have all of the ordered pairs. Okay, moving on to the next type of relation. Now, we are going to discuss about a very special type of relation which is referred to as the identity relation. What is an identity relation? So again, we're going to consider some arbitrary set A. So let A be a set. Then we are going to define a new relation IR. Let's call it IR. This is a set containing the ordered pair A, comma A such that A belongs to the set A, and we are saying that IR, this is a relation. This is a relation on A. This is a relation on A. Then in that case, IR is going to be referred to as the identity relation. Fine. Now, what does it mean? So let's try to understand this with the help of an example. So let's call it as R1. So we have a relation R1 such that it has got the elements 1, 1. Then we have the relation 2, the ordered pair 2, 2, and the third ordered pair 3, 2. This R1 is, let's say, is a relation on, it is a relation on the set A. It's a relation on the set A. Then R1 is going to be referred to as a relation. So A contains 3 elements. Let's call these elements 1, 2, and 3. Here we are saying that R1 is a relation on A. Now what is the uniqueness about this relation? Because here R1 is clearly, if we say that it is an identity relation, although we'll come to the identity part in a moment, R1 being a relation on A simply means that R1 is going to be a subset of the Cartesian product of A with itself. Now we know when we take the Cartesian product of A with itself, clearly these 3 ordered pairs 1, 1, 2, 2, and 3, 3 are also going to be member of the Cartesian product of A with itself. Now for it to be an identity relation, so if we pick up the element 1 from the set A, then the second element in the ordered pair must also be 1 as well. If we pick up the second element, which is 2, and try to form an ordered pair, then the second element must be 2 as well. So if we pick up 3, then the next element in the ordered pair must be 3 as well. Then in that case, the relation that we obtained, this is going to be referred to as an identity relation. Now let us suppose we consider another relation R2. Now R2 is a set which contains the ordered pair 1, 1, and we have 2, 2. What about this? Is R2 an identity relation on A? No. R2 is not an identity relation. So we have to be very careful here once we how we define an identity relation. So this is not an identity relation. This is not an identity relation on A. Why? The reason behind this, because the ordered pair 3, 3 does not belong to the relation, the set R2. It has to belong to the set R2, or only then we can say it's an identity relation, else it cannot be an identity relation. Okay, let's take another example. Let's say we have another relation denoted by R3 such that R3 has got the ordered pairs 1, 1. Then we have 2, 2. Next we have 3, 3. We have one more ordered pair. Let's call it 1, 3. Fine. So this is a R3 is a relation. The question is this an identity relation on A? Okay, this is also not an identity relation on A. This is not an identity relation on A. Identity relation on A, because what does the definition of an identity relation state? It states that A, A, it should be such that if the first element is A, the second element must also be A, and both of those must belong to the set A. So here we have 1, 1, that is fine. Then we have the ordered pair 2, 2, and next we have 3, that's fine. But here we have an extra element in R3, which is 1, 3. Now since 1, 3, although it belongs to the Cartesian product of A itself, but it belongs to R3. This should not have been the case. It should not have belonged to R3. Just because it belongs, so here we can say that R3 is not an identity relation, or it is only going to be a simple relation on there. It's not going to be that special type of identity relation. So that we have to be very specific here, that R1, R2 and R3 are all relations on it. All of them are relations on it. However, only R1 is the very special case where it's going to be an identity relation on A. Okay, let's move on to the next type of relation. Now the next type of relation that we have is referred to as a reflexive relation. So let's try to define what a reflective relation is. So let's say R is reflexive. We're saying that we have a relation R which is reflexive in nature. This means that it's going to be reflexive if and only if we have the ordered pair A, A belonging to R for all values of A, for all values of A belonging to the set A. That means we have some set A, we take its Cartesian product, and then we have a relation R which is a subset of A, a Cartesian product with A, meaning R is a relation on A. Then this R is going to be reflexive only if the ordered pair A, A belongs to R. That means, let's say we have a set A containing the elements 1, 2 and 4. Fine. Now going to define the the relation R such that we have 1, 1, 2, 2, and then we have 4, 4. And we are saying that this R is a relation, but it is a reflexive relation on A. So R is a reflexive relation on A. Reflexive relation on A. However, you might ask, like, then what is the difference between a reflexive relation and an identity relation? Because in that case also, here we have the first and the second element in the ordered pair same to each other, because there also we had the same ordered pair A, A for all A belonging to the set A. Now, the only difference between reflexive relation and an identity relation is in the previous example, if you remember. So here we considered R3. Now R3, if the set A contains the elements 1, 2 and 3, so we need the ordered pair 1, 1, 2, 2 and 3, 3. Now the existence of this extra element 1, 3 did not make it an identity relation. However, what happens in a reflexive relation, it does not care about this extra element. Even if it is there or not, it does not matter for a relation to be reflexive. That means as long as we have these three ordered pairs, then we can say R3 is going to be a reflexive relation. That means in our case here R, so let's call it R1. So here R1, which is denoted by this three ordered pairs, is going to be a reflexive relation on A. We can consider R2 to be containing the ordered pairs 1, 1, 2, 2, 4, 4, and then we have, let's say 1, 2, and we can have 2, 4. So the existence of these two ordered pairs is not a problem. Since we have these three ordered pairs, we can say R2 is going to be a reflexive relation on A. Okay, what about R3 that contains 1, 1 and the ordered pair 4, 4, and then we have, let's say 2, 4. Now, is this a reflexive relation? No, this is not a reflexive relation. This is not going to be a reflexive relation on A. Now, why is it not a reflexive relation? It is not a reflexive relation because 2, 2 is not a member of R3. We need it to be a member of R3. That means every element of A, if we pick up every element of the set A, 1, 2 and 4, its reflection must be present in that ordered pair. That means if we're taking 1, its reflection will be 1. We can think of in that particular terms. If we're picking up 2, the reflection must be 2. If we're picking up 4, its reflection is 4. Now in our case of R3, here we have the reflection of 1 and the reflection of 4 present, but the reflection of 2 is not present. We have 2, 4, not 2, 2. And because of this reason, R3 is not a reflexive relation on A. Okay, it's neither an identity relation nor a reflexive relation. So if we have understood reflexive relation, Now we can go ahead and say that an identity relation is a very special case of a reflexive relation, or we can say that all identity relations are reflexive in nature. Okay, let's move on to the next type of relation. The other type of relation that we will discuss now is referred to as the symmetric relation. So let's say we have a relation R on the set A. A relation R on the set A is said to be symmetric, in nature, or we can say symmetric relation. This is going to be a symmetric relation if and only if we have an ordered pair A comma B belonging to the relation R. This simply implies that B comma A must also belong to the same relation R for all values of A and B picked up from the set A. So A and B are elements of the set A. Whatever be the A values of A and B, if we have A comma B, the ordered pair A comma B present in the relation R, then B comma A must also be present in that same relation R. Only then we can say that R is a symmetric relation. For instance, let's say we have R1. So first we have to define A. Let's define A somewhere here. So A is a set containing the elements 1 comma 2. Fine. Now R1, let's say this is giving us the relation 1 comma 1, and then we have 1 comma 2, and then we have 2 comma 1. Now R1 is clearly a symmetric relation. This is a symmetric relation on A. Why is it a symmetric relation? So if we pick up the ordered pair 1 comma 1, this simply tells us that means if we interchange the position of the elements in the first position and the second position, this is going to give us what? This is simply going to give us again 1 comma 1, and both of these are present in R1. Fine. So if we take 1 comma 2, now what is its what if we interchange the position of the ordered pair? So we are going to get elements in the ordered pair. When they are interchanged, we get 2 comma 1, and we see that both of them belongs to the relation R1. So why R1 is a symmetric relation? Let's say we pick up the first ordered pair 1 comma 1. So clearly 1 comma 1 belongs to the relation 1 R1. So this simply implies that if we interchange the position of the elements in the ordered pair, that means this second element goes to the position of the first element, and the first element moves to the position of the second element. We again get 1 comma 1, and clearly 1 comma 1 belongs to R1. Fine. And then we have to pick up each and every element. So if we take 1 comma 2, now 1 comma 2 clearly belongs to R1. This implies that 2 comma 1, this ordered pair is also a member of R1. So that is why here we are saying that R1 is a symmetric relation on A. So can we not say IR is simply the identity relation, that all identity relations are going to be symmetric in nature, that identity relation is always a symmetric relation. It is a symmetric relation. Okay, now we will move on to the next one, which is an anti-symmetric relation. Now, anti-symmetric relation means, let's say we consider a set A. So let A be some arbitrary set. Let A be any arbitrary set, such that if we have the ordered pair A comma B belonging to a relation R, and at the same time we have B comma A also belonging to the relation R, this simply implies that A must be equals to B. Then in that case we say that the relation R is anti-symmetric relation, and A must be equals to B for all values of A and B belonging to the set A. That means any values of A and B that we pick up from the set A, it must be true that A equals to B. Then we can say that the relation R is going to be anti-symmetric in nature. So let's try to understand this with the help of an example. So let's say we have a relation R. So let's say we have a relation R. It's just a general relation for the time being, that R be a relation on the set of the natural numbers n. It simply means that we're saying here that R must be a subset of the Cartesian product of n with itself. Okay, so R is a relation on n, and this relation is defined by, so here we have x related to y, x r y, if and only if and only if x divides y, x divides y. Fine. So here we're defining a relation R such that x divides I, where x belongs to the set of natural numbers and y also belongs to the set of natural numbers. Now we're saying that R is an antisymmetric relation. Now the reason why we're saying that it's an antisymmetric relation, because think about it. We'll use this definition. So let's say for any two elements A and B, let's say for any element A comma B belonging to the set of natural number, if we are saying that A divides B, we're saying that A is dividing the number B and B also divides the number B, A. Then what does it mean? This simply means that A must be equals to B, right? If we take the help of some numbers, it will make more sense. So let's say we're saying here that 2 divides 2, and we have, again, we are going to interchange, then 2 divides 2 as well. If we're saying 2 divides 2 and 2 divides 2, this simply means that 2 must be equals to 2. In other words, that's what we're saying. So here, this is R is going to be an example of an antisymmetric relation. Now coming to the last type of a relation, referred to as the transitive relation. Now transitive relation can be understood with the help of an example. So let's say if we say A equals to B, we're saying that if A equals to B and B equals to C, then by the property of transitivity, we can say that this implies that A must be equals to C. This is a similar idea that we'll be using to define a transitive relation. Okay, so what is a transitive relation? Let's say let A be some arbitrary set. So let A be an arbitrary set. We are going to define a relation R on this set. Also let R be a relation. This is just a general relation. Be a relation on A. R be a relation on A. That means that R is a subset of the Cartesian product of A with itself. Now we are going to define the R as a relation on A in a very specific type of way. The relation being that if we consider one ordered pair A comma B belonging to the relation R, and at the same time we pick up another ordered pair B comma C belonging to the relation R, if this implies that A comma C belongs to the relation R for what? For all values of A, B and C belonging to the set A, then in that case we say that this relation R is a transitive relation. So this implies that R is a very special type of relation. So R is going to be referred to as a transitive relation. So this is the definition of a transitive relation. Okay, fine. Let's try to understand this with the help of an example. So here we have a relation R on the set of natural number n, and it is defined by the ordered pair x comma y belonging to the relation R if and only if x divides y for all values of x and y belonging to the set of natural number. We have to show that this R is indeed a transitive relation. So how shall we do that? So what we'll do, we're going to first consider three numbers. So let these three numbers be x, y and z, such that these are all natural numbers that belongs to the set of natural numbers, and x, y, z are natural numbers. And we're considering the values of x, y, z such that, let's say if we take x comma y simply belongs to R. What does it tell us? This tells us that x divides y, and we have y comma z. This belongs to the relation R as well. This simply means that y divides z. Now what does it mean when we say that x divides y? Now x comma y belonging to R, this simply tells us that x divides y. X divides y. Now if x is dividing y, can we not say that y is given by lambda times x? Well, lambda is some natural number. We don't have to worry about it. It's simply telling us that y is a multiple of x. If x divides y, that is the meaning of x dividing y. And we have y comma z belonging to R, the relation R, which simply means that y divides z. Now if y divides z, we can say that z is going to be some multiple of y. So let's call it beta comma y. Let's call it number 2. So lambda and beta, now we have to specify that what are lambda and beta, where we have considered lambda and beta to be some natural numbers. Okay, fine. Now we have here from 2. So from 2 we have considered that z is a multiple of y, so we have z equals to beta times y. Again, what is y? From 1 we can replace y with lambda times x, so z must be equals to beta multiplied to lambda times x. We have z equals to lambda times beta multiplied to x. Now lambda and beta are both natural numbers, so their product is also going to be some other natural number. We don't have to worry about this value, or what we can do is we can replace it with some other natural number, gamma. So z comes out to be equals to gamma times x, where we are considering lambda times beta to be equals to some constant lambda, which is a natural number. We don't have to worry about that value. All it says here that z being equals to gamma times x simply means that z is a multiple of x, or in other words we can say here that x is dividing z. So here this simply tells us that x divides z. So we started out by first considering x comma y belonging to R. That means x divides y and then y divides z, and we are able to show that x also divides z. In other words, what we have shown here, that if x comma y belongs to the relation R and we have y comma z also belonging to the same relation R, then this must imply that x comma z belongs to the relation R, and this satisfies the condition for transitivity. So this implies that R is transitive. R is transitive on, or you can say R is a transitive relation. This is a transitive relation on the natural number n. Now we are going to end the lecture by understanding equivalence relation. Now this is not a type of relation, this is more of a property. So let's say let R be a relation on, let R be a relation on A. It is a relation on some set A, and this R is going to be referred to as an equivalence relation. So R will be an equivalence relation, will be an equivalence relation on the set A if and only if it meets the following three criterions. If it is reflexive, if R is reflexive, if it is symmetric, if it is symmetric, and it is also transitive in nature, if it is transitive. If a given relation R on A is reflexive, symmetric, and transitive, then we can automatically say that R is going to be an equivalence relation. So here we have R, a relation on the set of all lines in a plane, and it is defined by the ordered pair L1, L2 belonging to R if and only if L1 is parallel to L2. Okay, let's try to understand the problem first, and then we'll try to solve it. So here we have a set A. So let's call it the set L be the set of all lines in a plane. So we have a plane and we are going to consider all different types of line that can be drawn on that particular plane. Now we have to form a relation using these lines, and we cannot pick up all the lines. We have to pick up only special type of lines on that plane. So we are going to pick up the lines such that if we pick up two lines L1 and L2, they are going to form an ordered pair L1 and L2 such that L1 is parallel to L2. Fine. So here L1 and L2 belongs to the set L. So let's also mention that where we have L1 comma L2 belonging to the set L. Fine. In other words, here what we have is a relation R that is defined on L. That means R is a subset of the Cartesian product of L with itself. Fine. Now, coming to the problem. So here, let us suppose we'll have to show that this is an equivalence relation. For that, first let's try to show that the given relation R is a reflexive relation. So how do we show that it is reflexive? Now here, let us consider a line L picked up from the set L. So here we're going to pick up any random line from that set L, because L contains the set of all lines in the plane. Now, can we not say that L is always parallel to L? That means a line is always parallel to itself. What does it mean? Now this simply means that the ordered pair L comma L is going to definitely belong to the relation R. It's going to belong to, here we are considering L1 and L2 to be the same line L. That means if L1 and L2 are the same line, then clearly we can say that L1 and L2 are going to be parallel to each other. So that means they must belong to the relation R. Now since we know that if L comma L belongs to R, what does it mean? This means that our relation R is reflexive in nature. So this is a reflexive relation. Okay. So we have tackled with the first one. Let's go to the second one, where we will show that the relation R is also symmetric in nature. Now to show that it is symmetric, we'll have to pick up two lines. So let's say we pick up L1 and L2. We're picking up L1 and L2 as two lines, and both belong to the set L, because L is the set of all lines in a plane. Now we are saying that L1 is parallel to L2. Now if L1 is parallel to L2, this implies that L2 must be also parallel to L1, right? That's a common sense. If L1 is parallel to L2, then it's definitely true that L2 is also going to be parallel to L1. Both of the lines are parallel to each other. Now what does it tell us? This tells us that if we take L1 comma L2, the ordered pair L1 comma L2 belonging to the relation R, and this is telling us that L2 comma L1 also belongs to the same relation R. Now this simply tells us that R is symmetric in nature. This is a symmetric relation. Okay, it's a symmetric relation. And then finally coming to the third one. So third one, what we'll do, we're going to consider three lines. So let those three lines be denoted by L1, L2 and L3. So let these three lines be picked up from the set L. Now we are saying that L1 is parallel to L2 and L2 is parallel to L3. This simply means that L1 must be parallel to L3, right? I can think of it this fashion. So here we have L1. First we are saying that L1 is parallel to L2, and then we are also saying that L2 is parallel to L3. So can we not say that L1 and L3 are parallel? Yes, definitely we can say that L1 and L3 are also parallel to each other. In other words, what we are saying here is that if we take the ordered pair L1 comma L2, it belongs to the relation R, and we are also saying that if we take the next ordered pair L2 comma L3 belonging to the relation R, this simply implies that L1 comma L3 also belongs to the relation R. Now what does it mean? So when this is the case, we simply say that the relation R is transitive as well. R is transitive relation as well. So here for this particular problem, we are able to show that the relation R is reflexive, it is symmetric as well as transitive. Since all the three relations are coming in place here, we can say thus we can say that R is an equivalence. It is an equivalence relation. So this brings us to the end of today's lecture. So we have discussed about different types of relation. We have talked about the identity relation. We have talked about the reflexive, symmetric, antisymmetric, and transitive type of relation. If a relation is symmetric, reflexive, and transitive, then in that case we say that R is an equivalence relation. We also talked about a void relation and a universal relation as well.